So this work was done jointly by AMD and Keysight Technologies. I am Kumar Saurabh, and I will be giving a brief presentation about our work. So for those who do not know about OpenFOAM, OpenFOAM is like a C++ code base that is used for doing fluid dynamic simulation, and it has been optimized mostly for distributed memory computing over the last decade. With recent advances in the modern architecture, specifically GPU, the community it has gained like a significant interest in optimizing this code base to the GPU. So there are two common approaches for porting the OpenFOAM on the GPU. One is like STD based offloading, and second is OpenMP based offloading. Both of these approaches it requires a minimal changes to the code, and this is very important for the obvious reason, like we do not want to like rewrite the full OpenFOAM, and it leads to a lot of issues related to maintainability of the code. So in this work, we have identified some of the key bottlenecks in GPU offloading of the OpenFOAM kernels, and we in this work we present a series of optimization that leads to a significant speed up on GPUs. So overall, we can see like as a result of these optimizations, we can see like we are able to get around 10 times 10x speed up compared to the CPU alone baseline. And this is a significant speed up for especially if we are doing some problems like we are interested in design or inverse problems. So this is a significant speed up that we can gain if we make use of proper optimization techniques on accelerators. So here, like I just want to focus on a very specific optimization that we did, which is related to kernel launch latency. So if we look at the GPU kernels that were dispatched by OpenFOAM, the workloads are mostly dominated by various small kernel launches. And what happens if you have a lot of small kernel launches, that the kernel launch latency begins to dominate. And within each of these kernels, we get very low flop to byte ratio. And so this is an example of the code from a turbulence k omega SST turbulence model. So here, like we can see, like we have a lot of mathematical operations that is happening on the geometry on the field variables. Like we have the multiplication, division, min, max. And if we look at the kernel dispatch of this code, we see that it leads to like a lot of small tiny kernels, and this is like more than 1,000 kernels that is being launched to just do this simple this calculation. And so in this work, like we showcase like how we can reduce these large 1,000+ kernels to basically just three kernels. And more importantly, we also see that our 34 millisecond time has now been reduced to like about 2 millisecond, which is like almost like 16 times faster time to solve. And this is a significant speed up if we are a significant speed up, and it leads to a very good time to solve. And more importantly, like we are able to achieve this by making very minimal changes to the code. So the difference between the left and right code you can see is like we have just added some .expr on the .expr with the variables. Then with such a minimal changes of the code, we are able to get such a significant speed up. Uh, so this is so here is like one of the optimization that I've just introduced. There are many more optimizations that we'll be talking about at ISC. So do visit our talk, and we will meet you at ISC. Thank you.